Welcome to another session on image compression. Today I'm going to discuss IGS coding. IGS coding stands for Improved Grayscale Coding. It is a lossy compression coding technique. It has the advantage that it can eliminate psycho-visual redundancies. Those are the information that are not visually important. It also has the advantage it can reduce or eliminate false contouring. False contouring can be understood from this image. The first image is that of an animal and its shadow. In the second image, the shadow appears to be the mouth, so therefore it is a false contouring. Let us take an example and understand how IGS coding is done. Let us compute the IGS code for the grayscale data 12, 12, 13, 13, 10, 13, 57, 54, and we'll also compute the RMS error and RMS signal to noise ratio for the decoded IGS data. The table here shows the different columns. The first column is the data. The second column is the 6-bit binary equivalent code of the data. The third column is the sum column, which is to be computed. So from the sum column we are going to come up with the fourth column, that is the IGS code. So let us go to the sum column. The technique of computing the sum is the lower 3 bits of the current data is added with the lower 3 bits of the previous sum and the new sum is generated. So for the first data 12, there is no previous sum, so we are going to take all zeros as the previous sum. So when we add all zeros to the 6-bit code 001100, we are going to get 001100, which is same. So the sum bits and the 6-bit code is going to be the same for the first data. For the second data, that is also 12, we are going to take the lower 3 bits of the sum, that is 100, and we are going to add it to the lower 3 bits of the current data, that is the 6-bit code of 12. By adding this, we are going to generate this new sum as 010000. So this technique is continued till the last. So the technique is take the lower 3 bits of the sum of the previous data and add to the lower 3 bits of the 6-bit code of the current data, and the new sum for that data is generated. A special case can be observed for the last but one row where the higher 3 bits are all ones. So for such a data we again add all zeros such that we get back the same data. So the 6-bit binary code for 57 is 111001, and the sum bits are also 111001. For the last data 54, the previous three sum bits are 001 is added to the lower bits of 54, that is 110, and we are going to get the answer as 110111. So this is how the sum bits are generated. From the sum bits we are going to eliminate the lower 3 bits. Why 3 bits? Because we are constructing a 3-bit IGS code. If you are going to construct a 4-bit IGS code, we have to take in terms of 4 bits. So here we are taking in terms of 3 bits because we are constructing 3-bit IGS code. So coming back, so from the sum bits, we are going to eliminate the lower 3 bits and take only the higher 3 bits as the IGS code. So for the first data 12, the sum bit is 001100. We are going to eliminate the lower 3 bits and take 001 as the IGS code. For the next, we are going to take the sum bits, and from that we are going to eliminate the lower 3 bits and the remaining higher 3 bits is 010. So 010 will be the IGS code, and so on. We are going to compute that is how we come up with the IGS code. For the decoding, what we do is we are simply going to append 3 zeros at the end of each of this IGS code. So 001 appended by 3 zeros is nothing but the decimal value 8. Similarly, 010 appended with 3 zeros is nothing but the decimal value 16. So like this, we are going to convert the IGS code into a decoded sequence as 8, 16, 8 and so on. So if you observe the error, the actual data of the actual first data is 12, but it is decoded as 8. The second data is 12, it is decoded as 16. So we are going to compute the error, which is the difference between the original data and the decoded IGS data. So we are going to compute the error and we are going to square that error, and that is the last column, that is the squared error. To compute the mean square error or the RMS, that is the root mean square error, we are going to sum all the squared errors and average it out and take the root of that. To compute the signal to noise ratio error, we are going to take the decoded sequence, square them, that is 8 square plus 16 square plus 8 square plus 16 square and so on. So the sum of that decoded sequence divided by the sum of the last column, we are going to take those two. So this, that is the decoded IGS is the signal, and the last column, the squared error, is the noise. So the decoded IGS will be the numerator and squared error will be the denominator. So we are going to divide that and compute the RMS signal to noise ratio.